I'm confused about the way we define the quotient, especially the second part, the n. So, for example, if we consider two vector spaces, each of them being equal to R, then
yes.
M would,
to the real numbers.
Yeah.
Okay.
Then the basis of M would be the whole plane.
Plane? No. What?
What does it be?
Oh, I'm sorry. So we're looking at N. So what's M? No, M is, no, plane is not the word. Right, so if you have the real numbers, then M has at its basis the real numbers. Every vector is its own. So M, right? The basis vectors of M are elements of the product. And so this is not M. This is a basis for M.
Yeah.
And the example you're looking at, you're saying that R is a basis for M.
So if we have two vector spaces, like V1 and V2,
Yes?
wouldn't it be then essentially the R2 plane, the basis for M?
So yes, the basis is would be the, yeah, if you have R cross R, right, then this would be a basis for M.
Yeah. And then what would be N?
What would be N?
Yeah.
I mean, it'd be what it says it is. So you're looking at now you're looking at pairs A comma B, right? So what we're going to say is that, so N, so you look at things like, let's see now, so you want A. So what if A is, instead of being A, what if it's A plus, alpha, let's say gamma A prime, comma B, right? Then what's that supposed to be equal to? What do you want that to be equal to?
AB plus gamma.
You want it to be AB plus gamma A prime B, right? Now, that's a basis vector of M. That's a basis vector of M, and that's gamma times the basis vector of M. So what I want to do is I just want to make this expression equal to 0.
Mm-hmm.
So that's a basis vector of N.
Okay.
Not a basis vector, I'm sorry, a spanning vector. This is an element of N.
Mm-hmm.
N is generated by all expressions like this. And what you do is you just take the set, just a ground set of just these pairs. But then there's no relations on those pairs, right? AB is not related to A to B. There's no relation. Those are just different basis vectors. So we need to declare separately that 2 times AB is equal to A comma 2B. That's another relation, right? Where you say that 2 times AB is equal to A 2B. You need to declare that separately because otherwise these are just 2 basis vectors of some vector space.
I see. Okay. Thank you.
Okay, so in general, we'd like to construct a basis of the tensor product. Right, so last time we proved that tensor products exist, but we didn't prove anything about them. For all we did, I mean, we proved there's a universal property, but that's just what a tensor product is. For all we know, the tensor product could just be 0. And all multilinear maps are just always 0, and so we're just proving lots of interesting theorems about the 0 vector space and the 0 map to it. So let's actually say something non-trivial about the tensor product. I need a lemma, which I'm going to use twice today. And it says that if you have a subset of a vector space, this is independent if, well, let's say if. The only if direction is also true, but we don't need it. There exists a linear map. Oh, whoops. That's the end of my half screen there. So then there exists a linear, there are linear functions, and let's call those things phi b, such that, well, phi b is going to be mapped from V to the ground field F and this is going to be for little b and big B. So I have my subset here. I'm going to want to be showing it's a basis, but part of that is showing that it's independent. And I suppose that I have linear functions that take the vector space to F, and I have phi v of B prime is delta B, B prime. So what that says is that if you look at, so you have a linear function for each element of B, and you evaluate it on the elements of B, and it's 1 on B and 0 on all the other B primes. That's what this delta B, B prime means. It means that this function is 1 when B prime equals B, and it's 0 when B prime does not equal B. So just think of it as a linear function that separates the various elements of B, right? You have a linear function that picks out B from all the others, from little b from all the others. That's the point. You should think of this as being the phis are basically a dual basis, right? If B were a whole basis, then this would be the dual basis. Okay. That's for all B prime in B. I will leave you to prove this. The proof is basically one line. You write down a linear combination of elements. You want to see whether, and you suppose the linear combination is 0. You need all the coefficients to be 0. Apply all little phi b's to them. It's going to return you each coefficient in turn until you get all of them have to equal 0.
What is that symbol?
Which one?
The D, I think.
This thing?
Yeah.
That's a lowercase delta.
Oh, it's delta. Okay.
So it says delta B, B prime. That's the people call it the Dirac delta function. It's 1 if B equals B prime and 0 if B is not equal to B prime. Okay. The proof for what it's worth is written in the notes, but it is just what I said. Take a linear combination, apply the phi b's. It tells you all the coefficients are 0. Okay, so suppose that now I have a basis VI for the vector space VI. I'm now in the situation here where I have a product of vector spaces, VI, and I'm going to look at a basis for each of these. So I have a basis VI for the ith vector space, and what I'm going to do is construct the following thing. I'm going to construct B1 cross up through BR. Okay, so this is now just the product of the bases. So the elements of this are just lists of, they are lists of elements of the V's. I'm going to put this on the next line so I can write things under it, or next to it. B1 cross up through BR. Then this certainly maps to T, right? This is a subset of the product. And so remember, the tensor product is going to be a set T. It's going to be a vector space T, along with a multilinear map from the product, right? So if you give me some elements of this product, if you give me any element of this product, then it maps to T. So I claim that the elements that come from here, which is a much smaller set than the product of the V's, right? That this maps to a basis for T. And furthermore, that map is a bijection. What's the map? Just for notation, it takes a list, B1, up through BR. Remember, this is an element in the basis B1. BR is an element in the basis BR. Yeah? And that's going to map to an element that I'm going to call B1 little tensor up to BR. That's what the map looks like. So this notation, this little tensor product thing, these are little tensor product symbols. If you like, they're O times, because it's an X with a circle around it. That's the O, and there's the times. It just says you're going to multiply the elements little b1 up to little br. You're multiplying them in some sense. So this says here's a list of R things in different vector spaces, and here you're going to be multiplying them. And the point about T is that it's the universal way of multiplying them. So it's the sort of the, if you had a product of the V's then it would be multilinear, because if you multiplied one of them by a scalar, then the scalar would come out front if this was just a product. And if you summed two of them, then the product distributes over sum, and so then you get these visualizations that look like this. So the tensor product is the universal way to multiply elements in different vector spaces. And this is just the symbol that we use. This little tensor product is just the symbol for if you gave me a list of elements in the B's, in the V's, capital V's, then their product in the tensor product is just separated by tensor symbols instead of commas. Yeah.
And this is an isomorphism?
It's a bijection. Right? So, I mean, it maps this way. Maybe you'd be happier if I'd written this as a double arrow like this to say it's a bijection. It's an isomorphism in the category of sets, if you like. Right? It maps to the map is really this way, right? The map is that way, but it's a bijection, so maybe, I can do it this way. That better?
Yeah.
Now it's an injection and a surjection onto a basis for T. Okay. Let's prove this. Let's actually do an example first. So if you take R2 cross, tensor R3, then this has a basis. How many basis elements does it have? 6. Okay, so what are they? Start listing them.
1, 0.
Oh, let me call the basis here E1 and E2. The basis here is E1, E2, and E3. It's perfectly fine to use the same symbols because the tensor product is going to have one on the left and one on the right. So now let's go ahead.
E1 tensor E1, E1 tensor E2, E1 tensor E3, and this.
And then we have E2 tensor E1, E2 tensor E2, and E2 tensor E3. Right? There we go. So the proof of the theorem. So any multilinear map on the product is determined, I claim, by the values on the product of the subsets BI. What do I mean by that? I mean that if you give me, I'm supposed to know that these things, so I'm supposed to say that these things span T, right? In order to know that some vectors span T, what I need to know is that if you have a linear map from T to something, then it's determined by the values on this particular subset of T. So whatever the image of B1 cross BR, capital B1 through capital BR, whatever the image of that product is inside of T, it is some subset of T, and I want to know that it spans. To know that it spans, it's enough to say that every linear map is determined by what it does to the image here. Right? It might be overdetermined, they might not be linearly independent, but at least if I know what it does to the product of the B's, then I know what it does to all of T. That's what it means to span. Okay, so I claim it's determined by the values on this product, so let's suppose that VI is the sum over all J. And here I have some notational difficulties. This is going to be alpha J, and now I'm going to look at Bj, but I don't want this to be V1. Right, so what I'm going to do is I'm going to look at V1, comma, up through VR, and I'm going to replace V1 with the linear combination. But the problem is when I do that, I have to make sure that I indicate that they're in the first slot. So this is going to be the B1Js. So these B1Js, these things are elements of B1, right? The basis for the first vector space. That's my notational difficulty, is that I have to remember, for the little b's, I have to remember not just which basis vector it is, but which vector space it was in the first place. Yeah, so this tells me which basis vector it is in the first basis. First basis, jth vector. Yeah, okay. So then what happens So f of v1, comma, well, whatever remains, what's that? That's equal to, because this is a multilinear map on the product, I'm going to see what happens when I replace v1 with this linear combination. Okay? So this is going to be f of, well, let me say this is going to be a sum, because it's multilinear. So v1, this is v1 expressed in the first base as b1, right? But because it's multilinear, I can now pull out the alpha j's and the sums and so on. So this is going to be a sum over all j of alpha j times f of v1j. Same stuff. Right? That's the whole point about it being multilinear, is that the linear combination that I had for v1 pulls out over here when you look at the image. So this f, this linear map f on the product of the v's, it's determined by what it does to the basis vectors, because if I have one of the vectors expressed as a linear combination of the basis vectors, then remember, if I knew what f does to something that has a b and another b and another b and another b, then I've determined what f does to everything. So it's this and the same for I greater than 1. Yeah, so the point is that if I want to know what f does to an arbitrary list of vectors, what I know is what it does to a list of b's, and that's enough. Because by multilinearity, I can just expand each of the v's as a sum of a linear combination of basis vectors, and then pull out the scalars. And so all I need to know is what f does to the various to the products of basis vectors. Fair enough? Okay, so thus, if I look at this set, what do I call it? B, let me call this set B, and it's going to be B1 tensor dot 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 tensor BR, such that BI is in capital BI for all I. This spans. Again, if you have a subset of a vector space, then it spans if and only if every linear map is determined by what it does to that subset. Now we have to show that it's uniquely determined. We have to show that this subset of tensor products of basis vectors is linearly independent. And that's what we're going to use the lemma for. Using this lemma is kind of fun. So what we need to do is we need to produce linear functions from t to the ground field that take the various values. So here we have a basis vector. It's supposed to be a basis vector, right? This notation capital B is correct. We want a linear function that takes this basis vector to 1, or takes this vector to 1, and takes all the other ones in the product of the various BIs to 0. How am I going to do that? Well, this is supposed to be a function from the tensor product to the ground field, right? How do you make any linear function on a tensor product? This is the moral of the story about tensor products. How do you construct a linear function on T?
You give it a value for every basis vector?
Well, you can give a value for every basis vector, but we don't know that it's a basis yet. Right? We're trying to prove that it's a basis. In general, in some abstract way, how do you construct a linear function from a tensor product? So why don't we do, let's do it now since it's going to be useful. So the universal property, and let's say it's redux, because this is the same thing, but again, and it says that multilinear maps from the product of the V's to another space W, whatever that happens to be, That's the same thing as linear. These are linear maps from the tensor product from I equals 1 to R of the VI to W. This is the moral of the story about tensor products, right? The moral of the story is that to construct a linear map from the tensor product to another space, what you need to do is construct a multilinear map from the product to that same space. So here I'm supposed to be constructing a linear map from T to the ground field, and it's supposed to take values on these certain basis vectors, on these certain vectors here. So if I'm supposed to be constructing a linear map from T into the ground field, what I'm going to be doing is constructing a multilinear map from the product of the V's to the ground field using this, right? This is what the universal property says. Okay, so how do I construct a multilinear map to the ground field? This is going to be sort of telling as to what multilinear really means. So let's suppose, for the sake of argument, that Fi maps Vi to the ground field F for all I, and let's suppose that that's linear. Okay, so I have a linear map from each of the vector linear maps from each of the vector spaces to the ground field. Let's set F to be F1 tensor Fr, and that's going to map the product of the Vi to F, and it's going to be defined in the following way. I want to take any list V1 up through Vr, and I want to map it to F1 of V1 times Fr of Vr, like this. And this is the product in F. Okay, I am literally multiplying the images. I have a bunch of linear functions from the various vector spaces to the ground field, and all I am doing is multiplying the images of these guys. Okay, remember, multiplication is multilinear. But if I multiply one of these factors by alpha, then alpha comes out. If I replace one of these factors by a sum, then multiplication distributes over it, so it becomes a sum. Yeah? That's the thing. This is where multilinearity comes from. It comes from being able to multiply the images of V1 up through Vr. When the target is F itself, I already know how to multiply, so I'm going to use that. So, what can you tell me about little f as a function from the product of the v's to f? What property does this map have? It is multilinear. F is multilinear. That's the key point. So it's multilinear, so it induces a linear map, F tilde, from T to F, and this is linear. So the idea is that this guy maps to V1 tensor up through VR, and that maps to there. This is our map that we call T. It's the map to the tensor product that just replaces every list with the element that has little tensor product symbols. And this is the map F tilde that's induced by the fact that this map F is multilinear. So this map is multilinear, so this map is linear. What are the values of F tilde on the various basis vectors? Just by inspection, what are the values? Oh, so we don't know what the F's are. I haven't told you what F is. Let's take Fi to be little vi star, right? And that's going to be in the dual basis, capital Vi star. And that's the dual basis. Right? Remember, capital BI is a basis of VI. So there is a dual basis, which says you take the, it's a linear function on VI that takes the basis vector BI to 1 and takes all other basis vectors to 0. Right? Once you choose a basis, there's such a thing as a dual basis. Okay, so the value of this is so if I take BI star of BI, that's equal of BI prime. Well, let's do it this way. Of BI, that's 1, but BI star of BI prime equals 0 when BI prime is a basis vector that isn't BI itself. Okay, this is what the dual basis is. It's a linear function that takes one of the basis vectors to 1 and all the other basis vectors to 0. Agreed that this thing exists? We proved this in like lecture 2 or something like that. Every basis has the dual basis. Okay, then what can you tell me about when you have an element of this product basis, capital B? What's the value of F tilde B? Right, so we're taking Fi to be Bi star for all I. So we're going to get our linear function F, and what it's going to do is it's going to take the value 1 on Bi, sorry, 1 on B1, 1 on B2, 1 on B3, and 1 on B4, and so on and so forth. But if you give me any other basis vectors, it's going to give me 0 at least once. So when I multiply them, it's going to give me 0. So how do I, when I multiply this, I'm going to get either a bunch of 1s, and there's exactly one way to do that, or it gives me at least 1 0. All the other ways do that. So this says that FB tilde has the property that it's a linear function from T to F with, what do I say? It says it maps B to 1, and it maps B prime to 0 for if B prime is not equal to B. And now we're done by the lemma. Okay? What we did is we constructed our basis to say, well, we take these tensor products of basis elements, and we know that they span because every linear function in the tensor product is determined by what it does to these, and they're independent because there's a dual basis that takes each of these to so where each dual basis vector takes one of these guys to 1 and all the other ones to 0. And that means they're independent. Okay. Now I'm going to raise this theorem, which I was trying to keep on the board for the proof. Okay, so corollary. What is the dimension of V1 tensor up through VR?
The dimension of V1 is the dimension of V2.
Yeah, so we're just going to take a basis of this one, and we're going to multiply it by a basis of this one times the basis of this one. So the dimension that you get is just the number of choices for this basis element times the number of choices for this one times the number of choices for this one. So that's going to be the dimension of V1 times up to the dimension of V1. So the tensor product is not 0. That's useful to know, right? Its dimension is the product of the dimensions. Good. Let's leave that up for a moment. So if you give me a V in R2 and a W in R3, this is not what the notes say, but doesn't the notes say, but it doesn't matter. Then what's the tensor W? So give me an actual V in R2, an actual vector, and we will calculate these things.
1, 2.
3, 4.
Okay.
3, 4, 5.
Okay. These are the real numbers, right? There are things that aren't integers. Give me things that aren't integers.
3.5, 4.5, 5.5.
Fun, interesting real numbers.
Square root of 2.
Square root of 2. Any others?
Pi.
Pi. Any others?
0.
0. Fair enough. That's actually not a bad one to use. It's good to have a 0 in there just so you can see what happens. I was expecting someone to say E, but that's all right. Doesn't matter. Okay, so now let's take V tensor W. So what is this? Right, it's going to be a linear combination of these. Yes? So how am I going to write this linear combination, by the way? What is well, I've kind of done it here. That was not intended, but it turned out that way. I wrote these in kind of an array, didn't I? Right? You can think of these things as multidimensional arrays. This is a two-dimensional array, right? But if I had R2 tensor R3 tensor R7, then it would be a three-dimensional array, and there'd be a 7 deep layers of these things, right, coming out of the board. So I can think of this basis vector as being, so E1 tensor E1, that's going to be 1, and then a whole bunch of zeros. Like this, for instance, right? I can just identify it with its location in this array. And I mean, really what this says is the basis that I'm looking at here, there are 6 items, and they are indexed by a two-dimensional array. So beyond that, I don't care how you sort of notate them, right? I can notate them by writing E1 tensor E1, or I can write this basis vector as this thing, right? It's just the first of the 6. Okay, so then what is V tensor W in this notation? What's the coefficient on E1 tensor E1?
Square root 2.
That's going to be 1 times the square root of 2, right? Right, because remember, V here, this thing, is equal to 1 times E1 plus 2 E2, and this one is root 2 E1 plus pi E2, and thankfully there's no E3, so I don't have to fit it on the board. Yeah, so now when I multiply these things, I'm going to multiply them in the usual way that I multiply things. This is a linear combination of stuff. I'm just going to multiply it by this linear combination of stuff, and then allow myself to take the constants, the scalars, out to the front. Right? It's going to, the sums, the multiplication can distribute over the sums, and the scalars will come out front. So I guess what I'll do is I'll first write it in this notation. So this is going to be 1 times 2 E1 tensor E1 plus, let's write it this way, plus, let's see now.
That's supposed to be a root 2, right?
Yes, it is. 1 times root 2, 1 times 2, root 2, yes, 1 times root 2, E1 times E1, E1 tensor E1, and then it's going to be 1 times pi times E1 tensor E2, right? And then plus 1 times 0 E1 tensor E3. Let's not forget the zeros, right? And then plus, and now it's going to be 2 times root 2 times E2 tensor E1 plus 2 times pi E2 tensor E2, and then it's going to be plus 2 times 0 E2 tensor E3. Okay? Or we can write this down in terms of these. It's going to be a linear combination of these. And which linear combination is it? It's going to be the one that has root 2 up there, a pi there, 0 there, and a 2 root 2 there, and a 2 pi there, and a 0 there. What is this matrix in terms of the two vectors here? It is close. It's W times V transpose, right? Oh gosh, did I get it wrong? This is, okay, these are going to be, let's see, vectors that we can multiply. So we can't multiply V transpose times W. Oh, sorry, it's going to be, yeah, V times, what did I write? It's V times W transpose. What did I write before? Was that not what I wrote? I wrote them backwards. It's this column times this row, right? Yeah, okay. And this, by the way, gets to the example that we did last time, that not every vector in here is a, not every vector in here is a product, is a pure tensor product, right? So they is decomposable. So this element is decomposable in the sense that it is a product of a V tensored with a W. But every time we do this, we're going to get a rank 1 matrix. But there are elements in this 6-dimensional space that are not rank 1 matrices. So they're not all decomposable. Okay, that's what we did last time. Okay.
So I have a question.
Go ahead.
So while we know, I see where this would satisfy the things we wanted to at the tensor product. Why do we know that this is like the good definition of what we want multiplying two vectors to be? Like why would we choose this over something else?
Because it's universal. So any other way that you have to choose it, by the definition of tensor product, by the universal property, if you have some other way of saying I'd like to multiply these vectors, then that's going to give you a multilinear map from the product of the V's to your object where you're multiplying these vectors, and that will induce a linear map from the tensor product to it.
So it doesn't so matter which one we pick, just so long as we pick one, and then that's going to be universal, is the idea.
You don't get to pick the universal one. The universal one is universal. It's unique up to unique isomorphism. So if you chose one that's universal and I chose one that's universal, then because yours is universal, yours maps to mine. And because mine is universal, mine maps to yours. And you can easily check that the composition of these two things are identity maps both ways.
So basically, so long as we prove that this satisfies the properties we want, we're good because of the universal property.
That's exactly right.
Okay.
Right, so we proved that it exists, so we know the tensor products exist. And so then once they exist, there's a unique up to unique isomorphism. There's a unique universal one. That's the tensor product. And now we can prove things about it because it's unique. So we know what its dimension is. And we know how to write down products of elements in there and so on and so forth. Yeah? Okay, let's do something that's, I find, even more interesting than just tensor products, which is exterior products, exterior algebra. So this is something that you actually have more familiarity with, even though it's, in some sense, a little bit more complicated. So this is exterior algebra. So an alternating operator B maps V cross V. So these are all the same V, so there's no indices there. There are copies of this. So I'm going to call this V to the product R. Okay, so I'm taking V to the R, but it's the Cartesian product of V with itself R times. The W is a multilinear map such that if you have linearly dependent then phi has to be 0 on it. This chalk is getting short, so I'm going to replace it. Makes it hard to write with. I think it's sufficiently short. You've seen a multilinear, an alternating operator before. Which one have you seen? Yeah, the determinant. What's the relationship between V and R in that case? Well, the V's always have the same dimension, right?
Well,
Because
yeah,
there's a bunch of copies of
The
V.
dimension of V should be R.
Aha, so R is equal to the dimension of V. Yes, okay. So for example, I'm going to state this in a funny kind of way. So the volume of a parallelepiped, extra points if you can spell parallelepiped on the first shot. Can I do it?
No,
Yes, I did.
I thought it was an O.
It's parallel.
Parallelepiped?
I think it is E. It's only L in my parallelogram.
Google
Yes,
says
it's E.
Okay, well then my multi-professor is all the time.
Yeah, it's an E.
It might be one of those words where there's an alternate spelling.
British American.
British mathematician.
Parallel.
It does not give me an alternate spelling. But it says a prism with 6 faces, all parallelograms. So it has the O in that anyway. Okay. So I get extra points, don't I? So vectors V1 up through, on V1 up through Vn, and those are going to be in Rn, right? So this n is that n. So what is this volume? So I'm going to claim that the volume is supposed to be 0 if the V1 through Vn are dependent. Right? So it says if they all lie in a hyperplane, then I want the volume to be 0 because it doesn't hold any water there, right? Okay, now I also want, because this is the definition of volume, I want that if I replace Vi, if I replace that with alpha Vi, what is that supposed to do to the volume? So if I scale one of the edges by alpha, what happens? You scale the volume by alpha. Okay, and that's going to be for all alpha. And R, by the way, that means that we're actually looking at signed volume, because if alpha is negative, then you have to get a negative volume. Perfectly good with that. What happens if I replace Vi with Vi plus Vj? Then what happens?
Then change it.
So you don't change anything. Why not?
You're just shifting it up on one axis.
Yeah, so the picture looks like this. So that's going to be Vi, and this is going to be Vj not equal to I. Right, so this is all the j's that aren't equal to I, and here we have Vi, right? What's the volume of this thing? It's the volume of the base times the height. Now, if I shift this to Vi plus Vj, right, then what I've done is I've moved this vector but parallel to this base. So the height's the same. Unchanged. Yeah? And one more. What is the volume of E1 up through En? I can declare it to be anything I want. What should it be? It should be 1, right? Because it's base times base times base times base times base times height, which is 1, 1, 1. Now, do you know something else that satisfies these properties?
Determinant.
Right. These are the axioms that define the determinant. Yeah, therefore the volume is equal to the determinant. These are the axioms for depth. So this implies that depth equals sine volume. Good. Yeah.
The absolute value of the determinant, isn't an alternating operator?
No. Why is the absolute value of the determinant not an alternating operator? That is, you're correct, in case people couldn't hear online. He said, so the absolute value of the determinant is not an alternating operator. That is correct. Why is it not alternating? That's correct, because it's not multilinear. Because if you put a negative in front of something, the negative should come out, but it vanishes. It disappears instead. It doesn't vanish. It doesn't go to zero. It just sort of gets nullified somehow. Yeah. Yeah, in general, things with positive values are never linear in any way. Yeah. Okay, so definition. The rth exterior power of V is a universal alternating gadget let's call it an operator. So what is the operator? So it's going to be wedge. So this is big wedge is what this thing is. It's going to be big wedge R, and it's going to map V product with itself, Cartesian product R times, and it's going to map to something called U. I'm going to call it in the end wedge R of V, but such that for all alternating phi, so phi is going to be alternating. So here we're going to have our phi, and it's going to map it to something W down there. There exists a unique phi tilde with phi being phi tilde of wedge R. So this implies that there exists unique this guy, and that's phi tilde. And that's going to be linear. So this is where do I put it? Okay. So it's the same diagram that we did for the tensor product. It really is just the very same diagram that instead of writing that phi is multilinear, I wrote that phi is alternating. That's the only difference. So it's the universal alternating thing that you can do with R vectors in our vector space V. Theorem, wedge R exists. There's a universal way to do this. The proof is shorter than last time because we have available the tensor product, right? An alternating operator is a multilinear map. Given that it's multilinear and we're supposed to be inducing something linear, then what we're going to say is that, oh, well, if I said multilinear instead, then I could just use the tensor product up here. But I want it to be also alternating, so I'm going to take the tensor product and then impose the alternating property. So I'm going to, so proof. Let's set U, and it's going to be called wedge R of V. And that's going to be V tensor R. Now I'm taking the tensor product. So it's going to be V tensor V, and there's R of these. Okay, so I'm going to take a tensor product of R copies of V, and then I'm going to mod out by the relations. It's going to say the span of V1 tensor up through VR such that 2 of the V's, or the 2 of the VI, are equal. Okay? So these are called R forms. Okay? So I'm just taking the tensor product, and I'm just declaring that you get 0 if 2 of the vectors are equal. Now, note, alternating says you're supposed to get 0 if the vectors are linearly dependent. Well, certainly if one of them is equal to another one, then they're linearly dependent, right? That's enough, though, to make it, and you'll see, it's enough to declare that they're 0 if 2 of them are equal. So, what can you tell me about this map? The map that takes, oops. Now we have a bunch of V's and wedges. V cross R, so this is the product of V with itself R times. And this is the wedge R of V. And it's going to take V1 up through Vn. And it's going to take it to V1 with a wedge up through V R. Typo. It is actually my color chalk is out, so I'll have to remember that. Okay, what can you tell me about this? This map. This is, by the way, wedge. That's what these little things are. They're wedges. What about this map? What do you know about it?
If any of the V's repeat, it's 0.
Okay, we certainly know that if any of the V's are repeated, then it's 0. What can you tell me about the map as a whole? Does it have any properties?
Isn't it anti-symmetric?
Say it again.
Anti-symmetric.
Anti-symmetric. Oh, multilinear implies anti-symmetric. Sorry, alternating implies anti-symmetric when the characteristic is not 2, which is why you define things in terms of things being 0 instead of things being negatives of one another. And you were going to say something about this map.
Yeah, but I feel like, wait, does it map the basis to the basis?
No, it almost can't, because I mean it's multilinear. So yeah, okay, I just answered it. This is multilinear, right? Why is it multilinear? Because it's the tensor product and then modulo some additional stuff. So this certainly does factor through the tensor product, right? So it's multilinear. Because it factors through. The tensor R, by definition, it factors through the tensor product, therefore it is multilinear, right? It's just a set map. It's a set map from the product, from the Cartesian product to this set, whatever it is. But this set is a vector space, and this vector space is a quotient of the tensor product. Therefore, it has a linear map from the tensor product, therefore it is a multilinear map from the product. It's alternating. Why is it alternating? And now I need to use the fact that if I have V1 being a sum of, let's say, j greater than 1. So suppose that these things are linearly dependent. So V1 is a linear combination of the others. We'll do the same. You can do the same thing when you take Vj to be a linear combination of the others, but the notation's worse, right? So it's just going to take V1 to be, right, not that much worse. It's just j greater than 1. I could say Vi is j greater than I, but or so, not equal to I. That's what I meant. Yes, thank you. So suppose that this is alpha j, vj, then plus v1 wedge up through vr, that's going to be the sum j greater than 1 of alpha j, and then it's going to be, we're going to have here vj, and then wedge v2 wedge up through vr. And what do I know that is? That's 0, because I explicitly modded out by things like that. Yeah, so you see the same trick, right? You're just imposing the relations that you want in the universal possible way. So what you have is that B maps B cross R to W. If that's multilinear, then implies that it factors, that B factors through B tensor R. And if it's alternating, that implies that it also kills this thing, which I'll call capital Y. Right? And so if it kills Y, that means that it factors through wedge R. So if you like V tensor R modulo Y. And that's it. Same argument that you had before. You impose the relations that you want, and that implies that every alternating map factors through this quotient, because the alternating map kills everything in these relations. Universal properties, very nice. Okay, example. What is, if you take V and W in R4, and let's take 2 column vectors, then what is V wedge W? Okay. Give me 2 vectors in R4. Give me 2 more entries. Give me 1 more entry.
Of the golden ratio.
Inverse ratio. Now, I don't care whether you put that in an exponent or not, right? Because phi inverse is 1, phi minus 1. Can I use one that's got only 1 symbol? Give me something that's easier to write down. You can make it 0 if you want.
0.
Wait a minute, I need 2 more. These have to be the same size. Minus 7. It is, but the minus sign might actually. We want to confuse things a little bit so we get things right. Yeah. Okay. So what's V wedge W? You're going to do the same thing that you did before, right? With the tensor products, because we know it's a quotient of the tensor product, right? And we know that we have a basis for this thing. So I know I can express this as a linear combination of things that look like, right? So this is going to be in the span of E1 wedge E1, E1 wedge E2, up through E4 wedge E4, right? It's going to be in the span of these things. So let me just write it out that way. Okay, so what's it's going to be now? Okay, it's going to be root 2 E1 wedge E1 plus pi E1 wedge E2 plus 0 plus phi E1 wedge E4. Granted? Okay, now what? Plus 2 root 2 E2 wedge E1, right? Plus 2 pi, you can read these out to me. This is going to be E2 wedge E2 plus 0 plus 2 phi E2 wedge E4. Thankfully, there is no 3 here at all. So, right? This may as well have been R3, wedge R3. That's totally fine. I'm good with writing fewer symbols. It's just, you know, just so we know. Maybe I'm going to change it up on you. The -7 and the 0. It hasn't come in yet, right? Because I haven't done the E3 wedge stuff. But I want to do something that'll make it not quite. Okay, so now we're going to get plus, so plus, if you like, -7 root 2. -7 root 2 times what? E3 wedge E1, is that right? And then -7 pi E3 wedge E2. There's no E3 wedge E3, and then it's going to be -7 phi E3 wedge E4, right? And then that's it? Nothing else? Agreed? Okay, so how should I gather these terms?
Well, E1 wedge E1 should be 0, right? And all the other ones are.
Those are 0 because it's alternating. What can you tell me about the relationship between this term and this term?
You should flip so 2 to E2 wedge E1 is negative 2 to E1.
Right, so E1 wedge E2 is minus E2 wedge E1. Why is that? No, it's not. You just said it's how I defined alternating. It's not how I define alternating. This is how most basic linear algebra books define alternating when the coefficients are real. When the coefficients are F2, this is the wrong definition. It actually gives you the wrong answer. It literally does give you the wrong answer. What we do know, however, is that E1 plus E2 wedge E1 plus E2, that's equal to 0. But what is this? It's equal to E1 wedge E2 plus E2 wedge E1. And the terms with 2 E1s or 2 E2s, those are both 0. That means this is that. Right? So this relation implies this one, but over F2 it gives you the correct answer. Whereas this one over F2 gives you the wrong answer.
I thought over F2, 1 equals -1. Or,
It does.
but I thought that was right, though. I thought.
Yes, yes, but if you impose this relation, you just get that E1 wedge E2 is E2 wedge E1. You can never conclude that E1 wedge E1 is 0.
I see.
You never get this relation out of this relation over F2. Right, so you have, this is the correct relation to use, and it implies this one, but over F2 it does not imply the other way around. Yeah. What? Okay, so we're going to rewrite this now. I know this is a little bit laborious, but it explains why alternating does what it does. So then how should I be gathering this? This should say, it should say pi minus 2 root 2 times E1 wedge E2, right? And then, let's see now, E1 wedge E4, so there's this one, and where's the E4 wedge E1? Well, there is none. Okay? Plus phi times E1 wedge E4 phi. E1 wedge E4. Yes, okay. Yeah, I'm looking at it, it's phi minus 0. These are determinants. Do you see these are determinants here? That's what's going on? Okay. Do I have to do the rest? How many of them are there? There are not too many. Let's see now. The wedge, the E2 wedge E4 and E4, oh, E4 wedge E2, there's nothing. So that's going to be plus 2 phi. E2 wedge E4. And then we've got the E3 wedge E1. I'm going to do that one like that. And E1. Oh, there is no E1 wedge E3. So this is going to be plus 7 root 2 E1 wedge E3. Right? And then we have that one, E3 wedge E2, and E2 wedges, so it's going to be plus 7 pi E2 wedge E3. And then we have the E wedge E4, the 3s and 4s. So it's just this one. So it's going to be minus 7 phi E3 wedge E4. Okay. So the only one we got was an interesting determinant, was this one. Okay. All right. So here's a proposition. I claim that V to W, this is linear. If this is linear, then it induces a canonical map. And it's going to be wedge R V to wedge R W. And I'm going to call this linear map wedge R phi. And what's it going to do? It's going to take V1 wedge up to VR, and it's going to map it to phi of V1 wedge up to phi of VR. So what we say is that wedge R is a functor. So this wedge R is the functor. And what that means is that in vector spaces, we have objects, those are the V's and W's. We have the morphisms, those are the linear maps phi. When you apply wedge R, you get an object, wedge R of V. You get an object, wedge R of W, and you get a morphism, wedge R of V. So it takes every morphism in this category to another morphism in the same category, actually, in this case. It's a functor from vector spaces to vector spaces. So that's just a comment about what that actually means. So the proof is in homework 5. And it even tells you what the entries of the matrix are. So if you gave me a matrix for phi, a basis for this and a basis for that, and then a matrix for phi, then it tells you what the entries of the matrix here are. Any guesses as to what they look like? If something is alternating, what do entries look like?
Zeros on the diagonal.
It's skew symmetric.
Skew symmetric?
Upper triangular.
Upper triangular?
Nilpotent.
Nilpotent? I believe all these things are no so far. I think every single one of them is no. So let's go on and you'll see. So that means it's a good exercise. Well, let's do the quintessential example. So the quintessential example is when V is equal to W and R is equal to n, and that's the dimension of V. So in that case, what we do is we define the determinant of phi maps V to V the determinant of phi is get phi, which is going to be wedge n. By the way, the determinant is, so this n is the top n you could choose. Wedge n plus 1 of phi, wedge n plus 2 of phi, those are all 0. So this is the top exterior power of phi. You don't know actually yet why this is the top exterior power, but when we write down a basis, you'll see why. Actually, it's not that, yeah, when we write down the basis, you'll see why, right? What would have happened if I had taken, 5 vectors over here? Then when I write down something in the product, it's going to be like E1, wedge E2, wedge E3, wedge E4, uh-oh. Now I have to choose another one, but there's only 4 of them to choose from, so I'm going to have one repeated. And that's going to make it 2. Okay, so if phi of Ej is Vj, which is the sum from I equals 1 to n of A, Ij, Ei, that's the ith column, the jth column of a matrix, of a square matrix, by the way, then wedge n phi of E1 wedge up through En, I claim that's going to be what? That's by definition V1 wedge up through Vn. Right? Those are the images of the standard basis vectors. Basis vectors don't have to be standard. What is that? That's going to be, which is going to be the sum from I equals 1 to n of A, I1, E1, Ei, wedge, wedge, sum from I equals 1 to n, and this is now going to be A, I, n, E, I, and that is going to be some coefficient. If you notice, see this product over here? This product is going to be some coefficient times E1 wedge up through En. Agreed? Because if you look at this product, what you can do is by multilinearity, you get to choose one of the E's from this one, and one of the E's from this one, and one of the E's from this one, and so on and so forth. If you repeated one, you get 0. So the only way that you can get something non-zero is by getting each of E1 through En exactly once in some order. But by this thing, you can rearrange them with a sign. So you're going to get some coefficient on E1 wedge up through En. Okay. What's that coefficient? Any guesses?
Some sort of determinant?
Some sort of determinant. How about the determinant of the matrix A? Right? You have a matrix A that has these entries. It's going to be the determinant of that matrix. Why is that? So this thing is actually, so this is what we want. That's that question mark is what we need. What it actually is equal to, it's going to be the sum over all I1 up through In of, oh boy, now my vision is not so good. This is going to be AI1 1 times EI1 wedge AIN 10 times EIN, right? That says you get to choose one of them, one of the E's from the first one, right? And one of the E's from the second one, and one of the E's from the third one, right? That's the choice of the one from the first one, the choice of the one from the nth one. That's what I've just written down here. And then you multiply the corresponding coefficients. So the point is that this is 0. So it's zero unless, it's zero unless did I write? Ij is pi of j for some permutation pi in Sn. Right, so the point is that in order for this to be a non-zero term, the I1 up to In has to be a permutation of 1 through n. Okay. So thus, V1 wedge up through Dn is equal to, here, is equal to the sum over all pi in Sn of, now it's just going to be A sub pi of 1, 1 times E pi of 1. I'm just rewriting this, but using I1 through In as a permutation of 1 through n. Okay? Wedge up through A pi of n, E pi of n, right? Now I want to rearrange these E sub pi. First of all, I can pull all the A's out, right? The A's come to the front, and then I'm going to rearrange the E's. So this is going to be the sum over all permutations pi in Sn of A pi of 1, 1, dot, 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 A pi of n, n, and then it's going to be E1 wedge up through En, but now I need a minus 1 to the pi. That's the sign that I get when I do the appropriate reversals. This is the determinant, as it turns out, of the permutation matrix pi, but whatever. It's just the sign that you get from rearranging these E's, which are in the I1 up through In order, rearranging to be E1 up through En. I get some sign, and there it is. What is this? That's the determinant of A. And what's this? I'm going to call that E sub bracket n. Now, let me give you the notation, and then I'll end, and we'll do the rest of it next time. The notation will make more sense. Being able to look at what's written over there. So the notation it says for sigma, what is sigma? Sigma is going to be a subset of 1 through n. So it's going to be S1 less than SR. And that's going to be contained in the set 1 through n. And if you give me a set E, which is going to be a list E1 up through ER, oh no, EN, I'm sorry, I want all n of them in V. You should think of these as being a basis, although they don't actually have to be. Let's set E sub sigma, little e sub sigma, to be E S1 wedge up through E SR. Okay? And it's important in this that we wrote the index set S1 through SR in increasing order. It just gives us a standard way to write these things, right? So the thing is that here I had a wedge product of n distinct basis vectors, but they were in the wrong order. So when I reordered them, I had a sign that came up. And I want to call this one E sub bracket n to say that's the standard way I want to write it. That's all this is. And let's just say that wedge R of capital E is going to be the E sub sigmas, such that sigma is a choice of R indices in 1 through n. So for instance, what's wedge n of E here? So I'm going to look at the exterior products of basis vectors. I'm going to do n basis vectors that come from E. Yeah, how many ways are there to choose n elements from an n element set? There's exactly one, right? So to say you were choosing n elements from an n element set, there's exactly one way to do this. And so this is just E sub bracket n. And that's all there is. There's only one way to do it. Okay? So what we did here is we said we were selecting, right, from this product here, we get to choose one of the E's, we get to choose another of the E's, we get to choose another of the E's, and so on and so forth. But they have to be distinct or they're going to give you 0. So what we're doing is we're choosing, so if I had only R of them, then I'd get to choose, I'd get to choose R of the E's total. And there would be n choose R ways to do that. Here, there's n choose n ways to do that, so there's only one. But you get to do it in all the orders, which is why you have to sum over all the permutations. Okay. So next time, we'll do the expected theorem, which is going to be that these things are a basis for the exterior.